Yeah, first of all, I want to thank the organizers for the invitation to give this talk here. So these are my collaborators. Theory was done at Duisburg-Essen, and the experiments were done at Darmstadt, and we also used published nuclear scattering data. And these are the papers. Outline, I will first give some background on chaotic scattering and then show how to calculate distributions with supersymmetry. Previously, one only calculated correlation functions. I will present some exact results for the distributions of the scattering matrix elements and the cross sections. And finally, I will compare with experimental data. So that is a picture. Waves propagate in fictitious or real channels. They are scattered at a target, so nucleus or disordered medium or whatever, here in the interaction zone. And the scattering matrix connects the ingoing and the outgoing waves. It is an M by M matrix if you have M channels, and flux conservation requires that it is unitary. So this way of thinking was developed in nuclear physics, but now it's applied in very many other fields, electron transport in disordered media, classical waves, and particularly wireless communication also. Yeah, here's some history, a very old picture going back to the 60s. Here you see a differential cross-section of this nuclear reaction. Chlorine-37 is bombarded with protons, and you look at the channel where you have sulfur-34 and an alpha particle coming out. And if you look at this as a function of the proton energy, we see that the spectrum changes quite a bit. So we come from a regime of isolated resonances into a regime where we have overlapping resonances, and finally very strongly overlapping resonances where the individual peaks in the cross-section cannot be related to individual resonances anymore, and that is called the Ericson regime. The governing parameter is the average resonance width divided by the average mean level spacing, so gamma over d. Okay, now very often the target is chaotic or complex in some sense, which means we can try to resort to statistical modeling. And a very beautiful approach is the so-called Mexico approach to chaotic scattering or to stochastic scattering. So we assume that the S matrix itself is a random object, so a random matrix, and max and minimum information principle then gives us some probability measure. You see it here. Beta just characterizes the symmetry class we are in. So if you have no invariance under time reversal, S is just unitary, beta is 2. If we have invariance under time reversal, we have to distinguish the cases with or without spin rotation symmetry. S is then unitary symmetric or unitary self-dual. Beta is then 1 or 4, and beta equal 1 is by far the most common case. As an input, we have the ensemble average here, and of course, when analyzing experiments, we assume that it's equal to the energy average. The trouble with this extremely elegant approach is that it's very difficult to incorporate a parameter dependence here. So for example, we don't know how this would depend as a function of energy. So therefore, we have to look deeper into the microscopic structure of the scattering process. So one can show exactly that the scattering matrix element from channel B to channel A is given in this form, intuitively very clear. We enter the system through channel B. W is a vector that couples to the bound states in the interaction zone. So that is then the matrix resolvent corresponding to that. That is a matrix, the Hamiltonian of the bound states. And this is, with an imaginary unit, the sum of all these coupling vectors, which eventually will produce the resonance width. And then we leave the system through channel A. Okay, the so-called Heidelberg approach is now to say, let's only assume that the interaction zone is random. So we take for the bound state Hamiltonian a random matrix, and we can take a Gaussian distribution, which is no restriction at all, because one can show that any distribution, whatever you like, will give the same result, provided it has no scale competing with the local mean level spacing. That is referred to as universality. Again, the same symmetry classes appear. So in a mathematical language, here for the Hamiltonians, we have the non-compact versions of the symmetric spaces which are introduced previously. These were the compact versions previously. Now, a lot is known about the spectral correlations using the supersymmetry method. So such things or higher correlation functions. And the trick is always the same. Write the matrix resolvents as derivatives of ratios of determinants. Use bosonic and fermions integrals to lift the random matrices into the exponents, and then you can do the ensemble average. And this has been extended also for a distribution of the diagonal elements of the scattering matrix. But unfortunately, this method does not work for the much more interesting quantity, the distribution of the off-diagonal scattering matrix elements. But I now show you a method which can handle that. So this is what we want. First, we want to calculate the distribution of the real or imaginary part of the scattering matrix. And we do it by writing down the characteristic function in a very particular way. S here is 1 for the real distribution of the real part and 2 for the distribution or characteristic function of the imaginary part. So we need to calculate this ensemble average. W here combines these two coupling vectors, and AS combines the resolvent and its adjoint to form a Hermitian matrix, which is quite important. Now the trouble is that G contains the random matrix we want to average over inverse. So we cannot do this integral. But we can apply yet another trick. We can do a Fourier transform in the space of the W's. And then we are left with this term here in which the random matrices, because AS is inverted, appear linearly. The price we pay is this determinant here, but this we can open up with anti-commuting variables. So with a vector of fermionic variables. And again, we find H linear in the exponent, and we can do the ensemble average. And then we can turn the wheel and apply everything what we know about the supersymmetry method. And this is then, after some Hubbard-Satanovich transformation and other tricks, is then the supermatrix model. So rho is a supermatrix. It is 8 divided by beta times 8 divided by beta. And if you look at it, then those of you who might have seen such calculations for correlation functions before will see, well, it looks very similar. Yes, the only difference is actually this term here. This is a term that breaks supersymmetry. I mean, it might sound a bit paradoxical, but you have to break supersymmetry to get non-trivial results. And this supersymmetry breaking term here is completely different as compared to the case of correlation functions. So that is really the only difference. Yep. My time is up, or? Okay, now let's turn the wheel further. And let's do the limit of infinitely many levels in the interaction zone. And this is done by a saddle point approximation for the supermatrix integral. We are left with rather complicated Goldstone modes. So this is a coset manifold in the superspace, a lot of technical details which I don't want to discuss in detail. And this is what we come up with. And this already gives very much the structure of the final result. We can also do all the remaining results up to 2. We are left with 2 ordinary integrals for beta equal 2 and 4 for beta equal 1. So the final result is about a page, lots of terms, but terms with a simple and very clear structure. You see it already here. So this gives you rational or algebraic functions. And this here are oscillatory functions and integrated over. So you know precisely which parameters are combined with which variables and so on, all these things. We have not exploited this information yet. So far, we have just taken this result that we get, evaluated it on the computer, compared with numerical simulations and also with experiments. And this is what I want to show you now. So we started with the question, how can we statistically understand the transition from the regime of isolated resonances to the Ericson regime of strongly overlapping resonances? In the Ericson regime, we can apply rather straightforward statistical reasoning and convince ourselves that the distribution of the scattering matrix elements, so the real or imaginary part, should be Gaussian. And the question is, how do we approach this Gaussian? So here you see our result compared with numerics for gamma over d of 1.3, which is well below the Ericson regime, and here of 7.2, which is on the onset of the Ericson regime. And here you see, well, these are Gaussians. That is a distribution, and that's the characteristic functions. But here you see we are still quite far away. For some reason which I cannot explain, which would interest me very much, it always takes much longer for the distribution of the real part to reach the Gaussian limit. I have no idea why. So that is one of the open questions here. Any case, we now understand how that happens. Now I show you a comparison of our analytical result with microwave experiments. Here you see the characteristic functions. Here we are at rather low frequency, so the gamma over d is very well in the regime of isolated resonances. And you see here the characteristic functions, very different from Gaussian, from the Fourier transforms of Gaussian or Gaussian-like functions. And let me emphasize that it's very easy to sample these experimental results here to get this picture. So it's nothing complicated about a characteristic function if you sample it from experimental data. But I also show you the distributions at higher frequencies. So we are here still in the regime of isolated resonances, and I guess you will agree that these are not Gaussians. Well, but very often we don't have access to the scattering matrix elements in an experiment. Mostly we can only measure the cross-section. The cross-section is the absolute value squared of the scattering matrix, which means if we want to calculate its distribution, we need the joint PDF of real and imaginary part. Now that looked like a rather complicated problem. First we didn't know how to solve that, and then we came up with a very simple idea. We just move our calculation into the complex plane of k. K was the Fourier coordinate, so we have a complex k now, and then we get this joint PDF. So everything what I told you, we can just replace a k with a complex k, and then we get the joint PDF apart from some trivial modifications. So let me show you such a joint PDF. Strongly isolated resonances, still isolated resonances. So here you see some peak which is very far away from the Fourier transform of a Gaussian. Here you see something where you might believe that if we crank up the gamma over d, that this will become a peak that upon Fourier transform becomes a Gaussian. So here we have now full control over this transition. And now the distribution of the cross sections. Here that is for microwave data, that is for nuclear data, this reaction which I mentioned. Gamma over d is 0.7 here and 1.2 here, so well below the Ericson regime. This here is 1 for the nuclear data, so these two pictures correspond to each other very much, and here gamma over d is 30, so we are deep in the Ericson regime. If the distribution of the scattering matrix elements is Gaussian, the distribution of the cross-section is an exponential, and that is what you see here. So it's interesting to see how these distributions deviate from the exponential. The characteristic quantity is a value of p at 0, because if that deviates from the 1, that indicates a difference from the Ericson regime. You see it here and here and here in the isolated resonances. It comes up very high, and we have a very, very steep distribution, which is quite different from an exponential. Yeah, I come to a conclusion. So we solved a long-standing problem within the Heidelberg approach. I showed you how to do a supersymmetry for distributions, at least in cases like this one here. I showed you the distributions for the scattering matrix element and cross-sections. We now also have, because we have the characteristic functions, also the moments, which are actually, there are some other experiments where you need these moments. We understand the transition to the Ericson regime. Now we can use Brouwer's proof, an equivalence proof. He has shown that if you take the Heidelberg approach, then you can use it to calibrate the Mexico approach. So from comparing Heidelberg and Mexico, you can get information about the parameter dependence. The integrals in the Mexico approach are unknown. Nobody knows how to do them, but now with our results, we also have a handle on the Mexico approach. Showed data comparison, and now we are working on applying all these results to condensed matter and wireless communication. Thank you very much for your attention.